SwayamPrabha. Digital India. Educated India.
So welcome to lecture number 17 of Statistical Thermodynamics for Engineers. So we have now found out what is the translational energy. Okay, let's write it down one more time. ETR is E1 plus E2 plus E3, which is equal to 8, sorry, equal to 8 squared 8n p to the power of 2/3 n1 squared plus n2 squared plus n3 squared. Okay, so v was equal to L cube, which is the volume of the cube, and n1, n2, n3 are translational quantum numbers. Okay, all right. So there are 5 important observations, as we said in the last class, that we can make. 5 observations. First, we can make. First observation, we note that these quantum numbers are generated automatically. So the quantum numbers were not ad hoc. Okay, they arose naturally from the mathematics of the problem. Okay, which is nice. So there is no ad hocism over here. So as we know from a classical perspective. Okay? So this particular motion, this translational motion, right? Okay, has 3 degrees of freedom. 3 degrees of freedom. Okay, so X, Y, Z, 1, 2, 3, whatever you call it. So one quantum number originates from each degree of freedom. Okay, nice. So one quantum number originates from each degree of freedom. So and each quantum number is used to identify the complete state of the system that we are concerned with. So that is good. So there is a little bit of a classical analog. The second part, most important, is that ETR, if we write it properly, is A is that constant Ni squared. So you can see more than one combination of 3 quantum numbers, okay, yields the same total energy, right? So as an example, say this combination, so total, say for example n1, n2, n3. So let's assume the triplets. So 2, 1, 1 and 1, 2, 1 and 1, 1, 2. These 3 gives you the same energy. This gives you the same energy. Nice. This gives you the same energy. But the individual quantum numbers are different. Okay? So you guessed it right. So this is some kind of a degeneracy of the system. So from the point of view of quantum mechanics, okay, this is a very common feature, and we have already have an idea of microstates and macrostate. So the total energy is like a macrostate. And how you possess that total energy in these three different ways, for example, here, this is some kind of the number of microstates, because it does not alter the total energy, but it alters the way that you possess that total energy. Okay, so the point of view of quantum mechanics, so the number of independent from the point of view of quantum mechanics, the number of independent eigenfunctions, okay, corresponding to a given eigenvalue, to a given eigenvalue, a given eigenvalue is called degeneracy. The number of independent eigenfunctions corresponding to a given eigenvalue is called degeneracy. Okay. So, for example, in this case, the degeneracy is 3. The degeneracy is 3 in this particular case. Okay. From the point of view of quantum mechanics, the number of independent eigenfunctions corresponding to a given eigenvalue is called degeneracy. In this case, for example, the degeneracy is 3. So more generally, okay, every unique combination of quantum number, every unique combination of quantum number, every unique combination of quantum number represents an independent eigenstate. Represents an independent eigenstate of the system. Each unique combination, so like 2, 1, 1, 1, 2, 1, these are unique combinations. Okay, so from this perspective, what we can say that energy level is like an eigenvalue, whereas energy state, which is like the microstate, these are the eigenstate. All right. Okay. So each energy level is defined by its eigenvalue, whereas each energy state is defined by its eigenstate, defined by its eigenvalue. All right. Now, the third point is that if you look at it a little bit more carefully, okay, so the point here is, say, E translational is proportional to h squared divided by 8n e to the power of 2/3. Okay, now if you look at it, this is the Planck's constant. Very low. So therefore, this is minuscule. Okay, this is minuscule. Okay, due to its dependence on the square of the Planck's constant. Okay. For this reason, the kinetic energy of any particle, regardless of its size, regardless of mass or volume, okay, appears continuous. Okay. So the spectroscopic evidence, so if you are looking for spectroscopic evidence, that means the discreteness of the lines, spectroscopic evidence of quantization comes from the internal energy modes. Internal, this is external, right? Translation, internal energy modes, vibration, rotation, etc. Not through this, not through the translation component at all. Okay. So the last one, the point that is that these three translational quantum numbers, these three translational, these three translational quantum numbers range from unity to infinity. The number of eigenstates. So since they range from unity to infinity, the number of eigenstates, this leads to the number of eigenstates available or accessible to translational energy mode. Is simply overwhelming. Okay, so if the cube is three-dimensional, as you can see, so its ranges, it has got a huge range. As a result of that, the number of eigenstates can also be huge in this particular case. So we got two things, like for example, the energy is minuscule and therefore it appears continuous, and therefore we need to take a look at the internal energy modes for evidence. Okay? And we know that n varies from 1 to infinity, and the energy levels are like the eigenvalues, whereas the energy states correspond to the energy states represented by these quantum numbers are corresponding to independent eigenstates of the problem. So we can represent each possible energy state by its own cube in a 3D space. So how to do that? Let's take a look at this. So these are the different quantum number space, N2 and 3. Okay. So this is a positive octant. Okay. So we represent each possible energy state by its own cube in the 3D quantum number space. Okay, so like an octant. Okay, right. Okay. So this is how the representation actually happens. So we represent each possible energy state okay, by its own cube okay, in 3D quantum number space. Got it? Okay. Quantum number space. All right. So if we say that ETR is equal to h square and v square. Okay, so for same ETR, because ETR should be the same, that is like a macro state. Okay, so the state must lie on the surface of a sphere with radius n equal to n1 square plus n2 square plus n3 square raised to the power half. N is positive, so therefore number of quantum states and E associated with E less than equal to R. So NE is therefore written as pi n cube by 6, which is also written as pi by 6, 8 m e to the power of 2/3 energy translation divided by h squared by 2. Therefore, E is 4 by 3, 2m h squared e by 2, v translational e by 2. Okay. Okay. So differentiating this, if you differentiate this, you will get 2 pi 2m h squared 3 by 2 v translational energy dr. This actually gives you the number of eigenstates per unit energy in the range ETR to ETR. Okay, so this is also called density of states. Okay, so this is also called the density of states. Okay, so therefore the number of quantum states available is given by this. So this is now quantum states, and so the numbers must lie on the surface of this possible combination of quantum numbers. Possible combination of quantum numbers. Must lie on the surface of the sphere with radius this. Right. So we take a small example here. Let's say hydrogen. Let's consider hydrogen at a temperature to 98 Kelvin. Okay, so ME energy TR less than equal to equation. Okay, where ETR average energy is about 1.5 kT. This is just an example. Hydrogen. So if you calculate this number, this is actually now therefore equal to 4 pi by 3 2m by h squared 3 by 2 d ETR by 2. Okay, So this will give you the value of Me is equal to 4 into 10 to the power of 24. 4 into 10 to the power of 24. So, but the number of hydrogen molecules, if you look at it, the number of hydrogen molecules, this is actually equal to 2.5 into 10 to the power of 19. That was from ideal gas law. Gas law. So one gets more than 10 to the power of 5 translational energy states per molecule. Okay, per molecule. This is outrageous, right? So that is the number of molecules, that is the number of translational stages that you are going to get. It essentially almost guarantees that any gas will satisfy the dilute limit. There are so many number of translational stages that are available. Okay. Now let's do an example. Consider a free particle within one-dimensional box of length L. So you have to determine the average observable steady state energy within this box. Steady state energy within this box. Okay, so for any dynamic variable, A, we already know the rule here for H. This is for the steady state energy, as we know. This is given as star H hat dx dy at star dx dy. Okay. For a free particle, V is equal to 0, and the Hamiltonian operator becomes minus h bar square by 2m into the Laplace. Okay. So therefore, h bar, this case becomes minus h square by 2m chi star chi dx dy dz divided by I star chi dx dy z. Okay, so this is equation. If you look at this, if you look at the wave number, if you look at chi I, you already found this, given by P by L to the power of Ni by psi by L. All right. This equation that we already knew. So this is what we found out from the boundary conditions. Mean energy becomes, so you have to just plug this in. H bar, therefore, H 0 to infinity star square shy by d square into dx becomes equal to r squared by 2m 2 by l in I by l square 0 to infinity sine square n by x by l dx. So if you evaluate this integral, okay, so this will give you h square by 4 I square n into l. Yes, you validate the calculation, right? Also equal to h square 8n by n square l square. Okay. So as expected, the mean particle energy for 1D box is identical to its energy eigenvalue. Identical to its energy eigenvalue. Okay. So this is consistent with our general expectation that this is what it should be. Okay. So we can see, so therefore the mean particle energy is this. So this is a one-dimensional thing, so we have done it with this I you can actually drop also if you want, but this I is equal to 1, there is only one dimension that is available. Okay. So this is identical to what we have seen from your quantum mechanics as indicated by your earlier equations. So like the total energy. Okay. So this actually completes the translational mode. So we have seen that there are many translational modes possible, and we have seen that the translational modes can have like these 3 quantum numbers, translational quantum numbers corresponding to its 3 degrees of freedom. There can be a very large number of energy states that can be available, and the energy value is nothing but the eigenvalue of this particular system. But the energy is very minuscule because it is dependent on h square, which is the Planck's constant, and therefore we need more, need to look at the internal modes if we want to have a good idea that how does to look for spectroscopic evidence of the same. So we will see in the next class where we will go through now the uncertainty principle. We'll start with the uncertainty principle in the next class. Thank you.